of your class number 2. So I think we skipped these questions in the class because they were proofs, and we concentrated on more descriptive side of exercises in class number 2. So let's look at question number 2 in class 2. Now it says, consider a model, so population regression equation here, yi equal to beta 1 xi plus ui, and so this is the population model, regression model, and we are asked to estimate beta 1 by minimizing the sum of squared errors. So again, minimization technique is from your calculus, so should be easy to do again, and we did something like this before in class number 1. Now we all know that sum of squared errors needs to be minimized so that the the regression line fits best to the data. Now, in other words, we need to minimize errors or make them equal to 0 if possible, but usually we try to minimize it and try to equate it to 0, but it is usually, we will still have some errors there. Now, so let's set up a function of beta 1, because we treat beta 1 as unknown in this case, so we'll set up a function of beta 1, sum of s of beta 1. So that's a function of beta 1, and then this function is a sum of squared errors function, so I from 1 to, so assuming there are n observations, and the errors are then ui, which is the actual data, minus the beta 1, population beta 1, xi, again data squared. So that's sum of squared errors here. So we usually, minimization technique requires that we have to take first derivative or partial derivative of this function with respect to beta 1 and then equate it to 0, solve for beta 1, and that's the estimator for beta 1 hat. Sorry, beta 1. Beta 1 is a population beta 1, but we need to estimate or find an estimator for this basically, and that's the solution then. So when you take derivative with respect to beta 1 of this sum of squared errors function, it is going to be, assuming that this summation is not present and this I is not present there, you just take derivative of this function, just like you say that this whole thing here. So let me use it slightly different. So let's say that here is the function. So this is the function we're looking at. So taking a derivative of this function, basically there's a square here, without this summation sign, it's fairly easy, isn't it? So you ignore i's and summation sign. So you take a derivative of this function as if you are, you do this derivative now as if you are taking the derivative of this function. So then what happens is that, so when you take a derivative, this 2 comes into the front, and then the function here, y minus beta 1 x, so there is no 2 anymore because 2 minus 1 just makes it 1, and then 1 we don't have to write. And then using the chain rule, obviously we'll be taking derivative of the inside function here, which is the well, this will be 0 minus taking derivative of this one, this expression here with respect to beta 1 then gives us then minus x. So then you times it by minus x. Now we'll put back all these summation operators, I equal to 1 to n, and each one of these run for I now. Well, each one, there are different observations, n of them, so I runs from 1 to n. Now what we can do here is, well, first of all we have to equate it to 0. Oops, it's like a heart shape, so we'll leave it like this. So now I equate it to 0, and well, there's minus 1, there's 2. If you, well, using the constant rule of summation operator, if you remember my first video, we take out of this summation operator minus 2, then you will get yi minus beta 1 xi minus, sorry, this is now x, so this is x now, equals 0. Now divide both sides of this equation by -2, then you get I equal to 1 and yi minus beta 1 xi. This is I here. So okay, I should just get rid of it. So it's equal to 0. Now we'll multiply, so factor in the xi, so open a bracket and factor in xi, and let's try to solve it afterwards. Now, so let's save some space. So this would imply then we'll have something like this: yi xi minus beta 1. Sorry, once we take the derivative, we will have to replace beta 1, because this is a population here, beta 1. We're looking at estimator of beta 1, so we'll put the hat. I forgot to do this. Well, that's something you keep probably getting used to now, by now. Right, so yeah, I factored in or multiplied in the xi's. Now what we'll have now is, let's now use the distributive rule of summation operator and then open the brackets. Then we will have y equal to 1 to n, so I equal to 1 to n, yi xi minus beta 1 xi squared equals 0. Now here beta 1 is a constant, beta 1 hat is a constant, so I equal to 1. So yi xi minus beta 1 then comes out of this summation operator. Since it's a constant, unknown, we don't, and it's not governed by I index here, so this is just 1 here, so it will be out of the summation operator. Then let's bring this into the other side of the equation and times both sides by -1. You'll then get this result. This hat is missing again. I equals to 1 to n. What is this? This is square here again missing. So xi squared equals sum of I to n xi yi. Now from here, if you divide both sides now by sum of xi's, then we'll get is beta 1 hat equals sum of xi yi over sum of, so this n xi squared. Now this is the answer to the question. So this is the solution of the equation. Well, this is also called estimate, least squares estimate of slope coefficient of beta 1. That's the answer. So if you have the data, you can plug in the data and run this in Excel, and you get a beta 1 hat for any sort of data, so long as it's more than 30. It has more than 30 data points. Now let's now consider number 3, question number 3. So that's the answer. So let's clean this now. I forgot to where it is. Yeah. Okay. So question number 3. It says it's fairly similar to this one, the question number 2. So question number 3. Consider model where population regression is beta 0 plus ui. So we have now only constant and errors. Then A is to estimate beta 0 by minimizing sum of squared errors. Now again, we'll define a function of beta 0 now this time. Function of, so S is a sum of squared errors. Sum of squared errors. Beta is basically beta 0 of function of beta 0. I should make it shorter, which is then going to look like this. yi minus beta 0, which is again similar to the one that we did before. So ui here is basically yi minus beta 0 now, so that's what it is here. And again we take partial derivative with respect to beta 0. So the s, oops, I should have done it slightly differently. It's basically, yeah, delta here, s delta beta 0, and then you'll have, now if you take derivative, this again 2 comes here to the front, minus beta 0, there's nothing there, there's 1 to the power 1, and then if you take derivative inside function here with respect to beta 0, then it will be minus 1 basically. And that's n here, y equal to 1, and we equate it to 0 with the beta here. Now it's an estimator now anymore, we'll just replace it with its estimators, or estimate in this case. If it is a number it will be an estimate, but we'll derive a formula in this case basically, that's why it's an estimator. Now if you do manipulation here, again minus 2 out, so minus 2 out, give with this minus 1 becomes minus 2, so that's equal to 0, right? So now divide both sides of the equation by minus 2, this will then cancel out, then you will have, if you use the distributive rule of summation, then you will have n beta 0 equals 0. Now let's bring this into this side, so, and then divide both sides by minus 1, then you will have this is hat here again. I keep forgetting these things, I should be careful here, and I'm just assuming that in case I take an exam myself I would probably fail if I don't realize this myself, right? Now here it is, and what we do here, well this one is constant, so you know that the first constant rule of summation operator tells us something interesting here. So this becomes basically n, so there are n of these beta 0 hats, so it will be, when you sum them up, it will be n times beta 0 hat equal, what is this? Well, this is governed by I, nothing changed, so I equal to 1 to n. Now to find beta 0 hat, then divide both sides of the equation by n, or multiply both sides by 1 over n, then you will have I equal to 1 to n yi, and you know that this is basically something interesting, isn't it? This is y hat, that is the sample mean of y, yeah, so sample mean of y, so that's y hat. So beta 0 is equal to y hat, and that's the answer, that's the solution to A, this A here. Now, and number 3, question number 3 has this B. Question B says, show that in this case, in this case, r squared is 0. R squared is 0, which means, well, when r squared is 0, the model doesn't have explanatory power at all. So basically, this model doesn't explain variations in yi. So B now. Now it's a bit difficult to write it in this way. We know that sum of squared errors, which is SB0 here, beta 0 is errors is equal to in the model, if you run a model by using a sample, then you will have this predicted, so estimated, not estimated, the sample sum of squared errors, which is equal then to, if you replace it with the sample equation, which is then will be, I should have written the sample equation, I'll do that in a minute. So So basically, when you run a regression, so I will make this in a write it. Your equation, sample equation, looks like this usually when you run it without x's in this case. UI hat basically. So I just solve this equation for UI hat. It will be yi minus beta 0. So yeah, well, I is here, so minus beta 0 hat. So that I just plug it in here, and then this square is missing, so we'll put the square there. So this is, oops, I should have taken the pen, sorry. So that's 2 here. Now given this, now we know what beta 0 hat is equal to from before, from here. So that's equal to y hat, right? So just we proved it, or we solved it, in other words. Then what is it looking like? So yi minus y hat, sorry, y bar in this case. And in the book, or this sum of yi minus y bar squared has a name. This is called total sum of squares, total sum of squares. Now what is this? This is basically, if you look at the graph, and well, I hope I can illustrate it nicely here. It doesn't do, and we have these dots all around here. This is basically x's, these are y's, and you have all this. Yeah, and in case, and this is your y equal beta 0 plus x, sorry, beta 1 hat x, and that's your regression here. Now then the mean of sample y's is then somewhere here, let's say. So it will go this way here, and this is y hat here. This is just a constant number, mean, right? So, and then the total sum of squares is basically the sum of squares of this point up and this. Let me this. So this is this point here. The distance here is the error bars here, errors basically. And here is the distance here, and then there's another one. Well, all of them has basically some sort of deviation from the mean y, and that is called total sum of squares here. Yeah, it's like your variance, yeah, estimator, right? So that is sum of squares. But in the OLS estimations, what estimators do is they minimize this sum of squares. Well, the errors here, basically sum of these errors squared, right? But here we're looking at this y bar, so y distance from each of these points to the mean of the y. Yeah, so that's at TSS, basically total sum of squares. Now what does it have to do with r squared? So r squared is basically, if you write it, is equal to 1 minus sum of squared residuals, which is sum of squared errors here. In the population case, this is residuals because we're using an estimate, a sample estimate, a sample regression here. So that's why it's sum of squared residuals is equal to 1 minus SSR over TSS. And we know that in this case, this TSS is equal to SSR. So 1 minus, if you put TSS here now, if you plug, since they are equal, we just proved, given that there is no x, then they are equal, then TSS over TSS equals 1 minus 1 equals 0. So you just proved that in a case where we don't have x's and beta 1 has a 0, in other words, our r squared will also be equal to 0. So that's it. So that was question number 3. Now we'll try to do something more interesting, intuitive, with an intuitive, well, easy to interpret example from question class 1 number 2. Right, so see you in a bit.